Hello dear student, welcome in the online lecture series. I am Dr. Balasaheb Pagar, working as a associate professor in chemistry. Srimati Vimlaben Khemji Tejukaya, Arts, Science and Commerce College, Deolal Camp, Nasik. Dear student, in the previous lecture, we discussed about the aldehydes and ketones. So in the previous lecture, we discussed about the introduction, nomenclature, synthesis and the reactions of aldehydes and ketones. So all these discussed in the previous lecture. So in the today's session, we discuss about the inorganic chemistry topic, that is a crystal field theory. So crystal field theory and valence bond theory or the molecular orbital theory. So in the previous year, we discussed about the molecular orbital theory, and in this syllabus there is a valence bond theory and the crystal field theory. So in this section we discuss about the crystal field theory and the introduction of the crystal field theory. So students must be learned about the assumptions of crystal field theory. So assumptions of the crystal field theory are different than the valence bond theory, and also discuss about the shapes of the d orbital. So d orbital, all these orbitals not in the same shape. So we discuss about the different shapes of the d orbitals, and also discuss about the group theoretical symbols. So group theoretical symbol used in this theory, different types of the symbols used in this theory. So crystal field theory, if we compare the crystal field theory and valence bond theory, which is depends upon the covalent bond or nature of the complex or formation of the bond with a central metal atom, that is a covalent bond, and this concept which is depends upon the hybridization, like sp hybridization, sp2 sp3, d2 sp3 or sp3 d2, like this. So in this theory, consider the ionic bond. So crystal field theory and the valence bond theory, major difference between these two theory is the in valence bond theory that is 100% depends upon the covalent bond, means that theory consider the formation of covalent bond, means the coordinate covalent bond. But the crystal field theory, this theory depends upon the ionic bond, means this theory not consider the covalent nature or covalent bonding. So this theory based on the ionic bond. The use of the hybridization is suggested by the Pauling, help to interpret the geometrical shape of the complex, but there were unexplained differences between the measured and calculated magnetic moment, means the valence bond theory not explain the magnetic property of all the complexes. The compounds were found which had the intermediate values of their magnetic moment. So this theory explain the magnetic property of the complex, and we know the magnetic property of the complex which depends upon the unpaired number of the unpaired electrons. The distinction between the ionic and covalent bonding, the complex is confusion, means the covalent bonding valence bond theory that explain the formation of the complex by using a covalent bond, means coordinate covalent bond. The difficulty arises over the interpretation of the geometrical shapes. So geometrical shapes of the molecule, that theory can explain the hybridization, concept of the hybridization, and by using the hybridization we easily find out the geometrical shapes of the molecule. Pauling ideas offered the little or no explanation about the absorption spectra of the complexes, but in this theory they explain the spectra of the complexes. Crystal field theory, this is the new concept. The new theory called crystal field theory was first introduced by the Bastian van Wyk in 1930 and applied mainly to the ionic crystals, because this theory consider the bonding nature between the ligand and the metal ion is the 100% ionic. OL was largely responsible for developing a crystal field theory. In the simplest of the problem concerned, the bonding between the central ion and the ligands regarded as a purely ionic, so that the forces involved can be little as a electrostatic forces. Mean the ionic bond, that is a attraction between the positive and negative pole, means the bonding which is due to the purely the electrostatic forces. This theory does not consider the covalent bonding. So, valence bond theory, which is completely depend upon the covalent bonding, while this theory consider only the ionic bonding. Such a limiting treatment is generally referred as a crystal field theory. The modified treatment, which include the covalent bonding, is called as a ligand field theory. So, modified theory that explain the covalent nature, that theory is known as a ligand field theory. This theory was used to explain the color and magnetic properties of the crystalline solids. So, most important application of the crystal field theory. So, this theory explain the magnetic property of the complexes. In assumptions of the crystal field theory, first assumption, in a complex, the transition metal ion is placed at the center and surrounded by the ligand. Means the metal atom which is always present at the center and which is surrounded by the electron donor atoms, that is known as a ligands. The ligands are either electronegative, means the ligands are the electron rich molecules that maybe have a negative charge, that molecules may be neutral like H2O, or that molecule may be having a positive charge on the ligand side. If the ligands is a neutral molecule, then the negative end of the dipole is directed toward the metal ion. So, metal ion is a always electron deficient and the ligands are always electron rich. So, ligands may be negative, neutral or the positive charge molecules that donate electron to the central metal ion. There is a no interaction between the metal orbitals and the ligand orbitals, means there is no interaction between the orbitals. The attraction between the metal ion and the ligand is purely electrostatic, that is 100% ionic. The electrons of the metal ion are repelled by a negative field of the ligands. So, electrons which is present in the metal ion, means the field orbitals of the metal which is repelled by the electrons which is present repelled by the electrons from the ligands, and therefore the metal electrons occupy those d orbitals, means the d orbital which is present at the axis and where the electrons are present, and because of the ligands, electronegative forces of the ligand, the electrons present along that axis which is farthest away from the direction of the ligands, means those d orbitals which are present on the axis, that electrons which are away from the central metal ion. The number of ligands and their arrangement around the metal ion determine the nature and the strength of the crystal field theory. So, number of the ligands means the nature of the ligand as well as number of the ligands that determine the nature and the strength of the crystal field. Means for example, coordination number 4, coordination number 6, the degeneracy of the d orbital of the free metal ion is removed by the ligands when a complex is formed. Degeneracy means equal energy orbital. So, in the free ion, all d orbitals are having a equal energy, but when the complex is formed, d orbital which is not in equal energy, they split into two sets, means the degeneracy of the orbital which is removed in the presence of the ligand field or in the presence of the ligand. Shapes of the d orbital. So, this theory depends upon the formation of bonding between a d orbitals. So, this theory mostly consider the d orbitals. So, d orbital having a 5 orbitals, dx square minus y square, dz square, dx, dxy, dyz and dxz. All these are the 5 d orbitals. So, shapes of the d orbitals are different. The d orbitals and their occupancy play an important role in the coordination chemistry. It is necessary to study their shapes and the distribution in the space. For example, the dx square minus y square and dz square, these two types of the orbital which are present on the axis, and the remaining orbitals means the dxy, dyz and dxz orbitals which are not present on the axis. All the 5d orbitals are not identical. So, all these orbitals are not identical because some of the orbitals which are present on the axis and some orbital which are present in between the axis, and also their shapes are different. The dx square minus y square and dz square orbitals form one set and their lobes lying along the mutually perpendicular x, y and z axis. Means these orbitals dx square minus y square and dz square orbitals which are present on the axis, while the another set, that is a dxy, dxy, dyz and dxz orbitals which are present in between the axis, means their lobes not present on the axis, but that is present in between the axis. So, this figure clearly indicates the shapes of the d orbital. First two orbitals, that is a dx square minus y square and dz square, their lobes present on the axis. So, this figure clearly indicates the lobes present on the axis, while the another set, that is a dxy, dyz and dxz. So, the lobes of the orbital which are present in between the axis, means x, y, z, these lobes present in between the axis. That is why the energy degeneracy of the d orbital which is removed in presence of the ligand field. So, in the crystal field theory, there is a two sets of the orbitals. First set, that is known as a T2G set, that is the orbitals having dx, the orbitals in this set there is a three orbitals dxy, dyz and dxz orbitals, while the another set, that is known as a EG set, that having orbitals dx square minus y square and the dz square. Means the EG orbital which are present on the axis and T2G orbital, their lobes present in between the axis. So, in this theory use the different types of the group theoretical symbols. So, dx square minus y square and dz square orbitals are collectively denoted as a EG orbital. So, these two orbitals known as a EG orbitals, and dx square, dxy, dyz and dxz orbitals are collectively denoted as a T2G orbitals. The symbol T stands T means the triply degenerate orbitals. So, T indicates three equivalent energy orbitals or triply degenerate orbitals, and E stands for a doubly degenerate orbitals, means two orbitals that having a equally in energy, mean dx square minus y square and dz square that having a equally in energy, that is why that is known as a EG orbitals. So, E stands for 2 and T stands for 3, means triply degenerate. The symbol G stands for grade. The orbitals is said to be grade if it is a heterosymmetric, that is it has the same sign of the wave function at the same distance in the opposite direction, means the G stands for the grade orbitals and U stands for the ungrade orbitals. The orbitals is said to be ungrade if it changes the sign of the wave function, means the sign of the wave function is different, then that is known as a U, or U stands for the ungrade orbitals. Degeneracy of the d orbitals which is removed in presence of the ligand field. So, that is known as a splitting of the d orbitals. If we see in this figure, the free ion, all 5 d orbitals having the equal in energy, because all these orbitals present in the same energy. But when the ion which is placed in the ligand field or in the presence of ligand, when the complex is formed, then energy of the all 5 orbitals increases. So, ion in this, that is known as a ion in symmetrical ligand field, means there is no formation of a bond, but ion in the symmetrical ligand field, that is why energy of all orbitals, all 5 orbitals increase. But when the complex is formed, the orbitals split into two sets, one set that is known as a T2G set and another set that is known as a EG set. So EG set means that orbitals present on the axis means x, y and z axis. That's why energy of that orbitals increases more because their lobes present in between the on the axis, while the lobes of the EG set orbitals which are present in between the axis, the energy of the orbitals not increase, means that is always present in the free state energy, means only the energy of the orbitals increase. Those orbitals which are present on the axis, the energy of that orbital increases. So this figure clearly indicates there is a splitting of d orbitals, means the degeneracy of d orbital which is removed in the presence of ligand field. So d orbital split into two set, EG set and the T2G set. So increase in energy which is determined, that is known as a delta 0. So difference between the T2G and EG orbital, that is known as a delta 0 or the 10 dq value, that is also known as a 10 dq. So 10 means the number of d electrons. In the free ion, the 5d orbitals are degenerate, means all these 5 orbitals having a same energy. So all these orbitals present in the same energy level, equal energy, and the electrons which occupy such orbitals do so according to the rule of maximum multiplicity, means the electron filling of the electrons according to maximum multiplicity. So once all the electrons entered in, single electron entered into the orbital, and then pairing is start, because all orbitals that having a same in energy degenerate, or all these orbitals are degenerate orbitals. Crystal field theory is basically concerned with the effect of different arrangement of the surrounding ligand on the energy of d orbitals. So this theory, which is basically depends upon the arrangement of the ligand around the central metal ion. The ligands exerts an electrostatic field which tends to repel the electrons, particularly the outer d electrons of the central metal ion. So outer d electrons which is repel more those orbitals present on the axis. This repulsion raises the energy level of the d orbitals of the central metal ion. If the d orbitals which are considered all like and the ligands field affected, then all in the same way. So d are those orbitals which are present on the axis, which are the energy of that orbital increases more, and the splitting is occur between the d orbitals and split into two set T2G and EG orbitals. So energy of the EG orbital increases. In fact, d orbitals are not all alike, means all d orbitals are not same. They form two groups according to their orientation in space. Those d orbitals lying in the direction of the ligand, means the ligand which is come from that side, and the orbitals which are present on that side, they repel more. Why that repel more? Because the electrons present in the central metal atom or d orbitals and the electrons present in the ligand, they repel with each other. That's why they repel more, means those d orbital which are present on the axis, that is a dx square minus y square and dz square orbitals which are repel more when the ligands approaches to the central metal ion. Those d orbital lying in the direction of the ligand are repel more and rise in energy with respect to those lying away from the d orbitals, means those d orbital which is not present on the axis, they away from the ligand, direction of the ligand. That's why the energy of that orbital is not increased. But those orbital which are present on the axis, energy of that orbital increases because there is a repulsion. So differentiated in the presence of the ligand. This effect is known as a crystal field splitting. So this is known as a crystal field splitting, means the splitting of the d orbital into the two sets, that is a EG set and T2G set. This concept is known as a crystal field theory. By preferentially filling the low-lying d orbitals by electrons, the complex may be stabilized. The gain in bonding energy achieved in this way, that is known as a crystal field stabilization energy, means the filling of the electrons in the Eg orbital or the d2g orbital, which is again depends upon the nature of the ligand. So, application of the crystal field theory toward the octahedral complex, square planar complex and the tetrahedral complex. So, first consider the octahedral complexes. In an octahedral complex, it is assumed that the metal in the crystal in the center of the octahedron and the ligands which are surrounded at the corners of the octahedron. Means when the complex is formed, metal always present in the center and at the sixth corner there is a ligand. So, that is known as a octahedron, means the ligand which are present at the corners of the octahedron, while the metal ion which is present at the center of the octahedron. The Eg orbitals means dx square minus y square and dz square are directed along the axis, and the T2g orbital which are present in between the axis means x, y and z axis. It follows that the approach of 6 ligands along the x, y, z and minus x, minus y and minus z direction will increase in repulsion, will increase the repulsion and the energy of the T2 dx square minus y square and dz square orbital, which point along the axis much more close as compared to the dxy, dyz and dx square, dz square, dx xz orbitals, which point in between the axis, mean these orbital T2 orbital which are present in between the axis. That's why energy of these orbitals not increase. So, this is the crystal of the octahedron. So, metal atom which is present at the center, and while the 6 ligand which is present at the octahedron or the corners of the octahedron. Thus, under the influence of the octahedron ligand field, d orbitals of the metal split into 2 groups of the different energy. The average energy level of the average energy level, that is known as called as a barycenter. Means the energy of the Eg orbital increases from the barycenter. The difference in energy between the two set, that is a T2g set and Eg set, that is known as a delta 0 value or the 10 dq value. So, 10 dq which stands for 10 means that 10 indicates the number of d orbital, d electrons, means the d orbital that having a 10 electron, that's why the number is 10. So, number of 10 number of d electrons, d means the destabilization of the d orbitals, means d orbital which is not present in the same energy. So, split into 2 set, that is known as a destabilization of the d orbital, means split into 2 orbitals, or sorry, split into 2 groups, and q is the charge of the ligand. So, q indicates the charge of the ligand. If the ligand field is stronger, then splitting is more, and if the ligand is weaker, then splitting is lower. That is known as a strong ligand field or the weak ligand field, or strong field splitting or the weak splitting. Electron pairing energy means the electron which is paired at the lower energy orbital, or maybe the electrons which is enter first into the higher energy orbital. So, pairing energy of the electron can be defined as the energy required to transform 2 electrons with a parallel spin in different degenerate orbital into the paired electrons, that is in the anti-parallel spin. Means according to the maximum multiplicity rule, electrons first enter into the lower energy orbital with a parallel spin. Means the orbital that having a lower energy, means for example in the T2g orbital, first 2 or 3 electrons enter into the T2g orbital, and if the splitting is less, then the remaining electrons that enter into the higher energy orbital, that is a Eg orbital in a same spin, means same direction. But if the splitting is more, then electrons which is paired into the lower energy orbital, so that is known as a paired electron pairing energy. So, alternatively electron spin pairing energy is the transition from the parallel spin to the anti-parallel spin. So, parallel spin that convert into the anti-parallel spin, that energy known as a pairing energy. The pairing energy P depends upon the repulsion between the electrons occupy the same orbitals, that is the 3d orbitals, 4d orbitals and 5d orbital. Due to the decreasing electron distances between the main remain almost the same in the period. Means the splitting of the d orbital, which is not only depends upon the ligand field, but which is also depends upon the central metal atom which is present and the 3D, 4D or the 5D. And we know the splitting pattern is more in presence of a 5D orbitals. 5D, which is splitting of the d orbitals, is more. That's why the lower means the weak ligand field that may be form a square planar complex in case of a 5D orbitals, 5D central metal ion, and the 3D orbitals means 3D that is the central metal atom which is belong to the 3D transition series, means scandium to zinc. Strong field and weak field means if the ligand which is very stronger, for example cyanide, and if the ligand is which is very weaker like H2 or the Cn minus, these ligands are weaker ligand, the splitting pattern is less, and in presence of a stronger ligand that is a cyanide, splitting pattern is more. In an octahedral complex, if the value of 10dq is large, it is called as a strong field splitting, and the complex is referred to as a strong field complex. So such type of the complex is formed when the ligands are very stronger, or the central metal atom which is belongs to the 5D series. If the values of 10dq is small, it is called as a weak field splitting, and the complex is referred to as a weak field complex. Means if the ligand field is weak, or the metal atom which is belongs to the first transition series, that is a 3D series. So strong field 10dq value which is depends upon the strong field or weak field. So weak field splitting, the 10dq value is very small, so the electrons enter into the lower energy orbital as well as higher energy orbital, then pairing start. While in the strong field, the difference between T2g orbital and EG orbital is more, means the energy required to pair up the electron is small, that's why electron pair in the lower energy orbital. So this is the filling of the electrons in the low energy orbitals. Okay, so in the first figure that indicates the electrons first enter into the higher energy orbital, then pairing start. While in the low spin, the electrons which is enter into the lower energy orbital, then enter into the higher energy orbital, then pairing start. So magnitude of 10dq which is depends upon these three factors: the nature of the ligand, means the ligand is a strong field or weak field. For cyanide is the very stronger ligand and chlorine is a weak ligand. The splitting pattern which is depends upon the nature of the ligand. The charge on the central metal atom, means this central metal atom, for example central metal atom is a Fe, Fe2 plus and Fe3 plus. Splitting pattern is different. Whether the metal ion which belongs to the first transition series, second transition series or the third transition series, means all these factors are very important in the strong ligand field or the weak ligand field. Ligands which cause only a small degree of the splitting are termed as a weak ligand. Means if the splitting pattern is more, 10dq value is small, that is known as a weak ligand field. And if the splitting pattern is more, means 10dq value is more, that is known as a strong ligand. So cyanide, nitrate, these are ligands are very stronger ligands. So splitting pattern is more, that is known as a strong field complex. And the iodine or chlorine or bromine, where these ligands are weaker ligand, splitting pattern is less, that is known as a weak field complex. So in this session we discuss about the degeneracy of the orbitals, then group theoretical symbols and the assumptions of the crystal field theory. So student, solve following questions on the basis of this lecture. What is crystal field theory? What is meant by crystal field theory? Explain the splitting of d orbitals. So student must explain the splitting pattern of the d orbitals. D orbital split into two set. So degeneracy of the d orbital which is removed in the field in the presence of ligand, and give the assumptions of the crystal field theory. So assumptions of the crystal field theory which is different. So most important assumption of the crystal field theory. So this theory consider the 100% ionic bonding. Okay, so in the next lecture we discuss about the applications of the crystal field theory toward the octahedral complex or the tetrahedral complex or okay. So in the next lecture we discuss about the octahedral complex or the applications of the crystal field theory toward the octahedral complex. Okay, thank you very much.